Hi friends, in the context of Turing machine, let us discuss the concept of decidable and undecidable. Let us see decidable and undecidable problems. A problem is called decidable if we can find a solution to the problem and also construct algorithms to solve the problem. For example, check whether the given number is prime number or not. So for this problem, we can find a solution and also construct an algorithm. Check whether the given string is accepted by DFA, deterministic finite automata, or not. So these two are example for decidable problems. A problem is called undecidable if we cannot find a solution to that problem and also cannot construct algorithms to solve the problem. Example, halting problem. Let us see what is a halting problem. The halting problem is an undecidable problem in computer science proven by Alan Turing, which asks whether a given Turing machine will eventually halt, that means finish running, or continue to run forever, that is infinite loop, on a specific input. Let h be a function that takes two inputs, a program and an input I. The function h of pi outputs yes if the program p halts when given input I, otherwise it responds with no. That means we want to write a function or program h which is able to detect whether a program p with an input I will eventually halt after certain number of steps or it continues forever, that means infinite loop. Proof of halting problem is undecidable. Can we write a computer program called H that will determine if any program P halts or not? H of P will output halts if program P halts. H of P will output P will not halt, that means enter into infinite loop if P does not halt. Let us prove by contradiction. Let us have a hypothetical program D operates on H of P. If H of P halts, then it enter into infinite loop. If H of P enter into infinite loop, then it stop. That means the D is the reverser. That means it reverses the result. If H of P halts, it says it enter into infinite loop. If h of p enter into infinite loop, then it is stop. So now, if we give the program D itself as input to the program D, what happens? If D halts means, but actually the program does not halt. Like that, if D does not halt means, but actually the program halt. So, what we conclude, our basic assumption that program to predict halt does not exist. Let us see another undecidable problem. It is post-correspondence problem. The post-correspondence problem is a popular undecidable problem. It was introduced by Emil Leon Post in 1946. We are given a collection of dominoes. That means we can assume it like a tiles, each of which contains a string on each side, that is top and bottom. So as shown in below, that means T1, T2 and so on Tk and B1, B2 and so on Bk. So these are all strings. So our task is to determine whether a match exists. So what is a match here? A match is a sequence of dominoes, that is I1, I2 and so on In. That means you can organize these tiles in any order and each tile may be used any number of times, such that the string generated by reading all the symbols on the top side, that means on the top is identical to the string of symbols on the bottom. So that means TI1, TI2 and so on, TIN is equal to BI1, BI2 and so on, BIN. Let us take an example for the given set of dominoes, that is tiles, with these strings on the top and these strings in the bottom. So the following sequence is a match. That is, when you read the string on the top and also the bottom, it is same. For example, both the top and bottom strings matches with each other, that is A, B, C, triple A, B, C. So here also A, B, C, triple A, B, C. So this is what we say post correspondence problem. Though we were able to find a solution for the previous sample problem, but there is no algorithm to find whether a solution exists for the particular set of dominoes. Hence, post-correspondence problem is undecidable. But remember that not all dominoes need to be used. That means we can use only the selected from the given set. But each domino can be used more than once. But what is the condition to be satisfied? When you read at the top and when you read at the bottom, both should be the same. So the post correspondence problem is undecidable for the number of alphabets, that is alphabet set greater than or equal to 2.